Imagine you flick a switch and in a fraction of a second, a lamp across the room hums to life. We've all been taught the same common sense explanation. The battery or wall outlet pushes electrons through the copper wire like water through a garden hose, and those electrons carry the energy to the bulb. It is a beautiful, logical, and intuitive model. It's also almost entirely wrong. Welcome to Fighting Assumptions. Today we're dismantling one of the most stubborn misconceptions in physics, the idea that electrical energy is contained within the wires themselves. Most people assume energy is transported by the physical movement of electrons, but there is a massive problem with this analogy. Electrons are incredibly slow. The drift velocity, the actual speed at which an individual electron moves through a copper wire, is typically only a few millimeters per second. If energy were truly inside the electrons, it would take hours for your lights to turn on after flipping the switch. Furthermore, according to the laws of electrodynamics, the net energy flow inside an ideal conductor is exactly zero. The wires aren't the carriers of energy. They are merely the rails that the energy follows. The real magic of energy transfer happens in the empty space around the wires. According to Maxwell's equations, whenever an electric circuit is active, it creates an electric field from the voltage and a magnetic field from the current. Energy flows in the direction where these two fields intersect, represented by the pointing vector. This vector points from the source to the load through the air, or the insulation surrounding the wire. The copper wire is essentially a guide that tells the electromagnetic field where to go. The energy isn't sloshing inside the metal. It's an invisible aura of power hugging the outside of the cable. In 2021, the science channel Veritasium pushed this theory to its limit with a thought experiment. Imagine a circuit with a battery and a bulb separated by 1 meter, but the wires connecting them extend out into space for 300,000 kilometers before looping back. How long does it take for the bulb to light up? While common sense suggests it would take at least a second for electricity to travel that length of wire, the physics reality is roughly 3.3 nanoseconds. Because the energy travels via fields in the air between the wires, the bulb receives power across that 1 meter gap almost instantly. It doesn't wait for the electrons to do a 600,000 kilometer round trip. If energy flows in the space around a wire, then the space itself becomes our most important piece of engineering. When you look at a high voltage transmission tower, you aren't looking at a structure designed to keep electricity inside a cable. You are looking at a carefully calculated buffer zone for a massive electromagnetic energy storm. By suspending cables high in the air, engineers use the atmosphere as a primary insulator. We keep these energy rails far enough away from the Earth to prevent the fields from leaking or jumping tracks. This also explains the bird on the wire. When a bird sits on a single cable, both of its feet are on the same conductive rail, meaning its entire body is at the same electrical potential. To the electromagnetic field, the bird is just a tiny, harmless bump on the track. The power continues to scream past it at light speed. The danger only arrives if that bird becomes a bridge. If its wing touches a different wire or the metal tower, it creates a shortcut for the fields to reach a lower potential, with catastrophic results. This field theory is also why your extension cord has a warning label about coiling it. When you bundle a cable under high load, you are manipulating these electromagnetic fields. Coiling a wire creates an inductor, forcing the system to work harder and generate more heat. Because the energy is in the fields outside the wire, the heat becomes trapped in the insulation where the fields are strongest. A coiled cable reel can literally melt from the inside out because you've created a high-density energy zone with nowhere for the heat to escape. Ultimately, it's time to retire the garden hose analogy for good. To truly understand our world, we must stop viewing power cables as tunnels and start seeing them as rails. The energy doesn't squeeze through the copper. It rides the fields in the space surrounding it. While the electrons inside the metal are slouching along at a few millimeters per second, the actual power is screaming past them on the outside at nearly the speed of light. Your cables aren't pipes carrying a liquid. They are the conductive tracks that guide an invisible electromagnetic payload. When you flip a switch, you aren't just starting a flow, you're providing the track for an energy storm that inhabits the very air around the wire.